Hello, my name is Masaharu Akagi. Today, I talk about robust response with a checkerboard domain configuration in LES of stationary homogeneous isotropic turbulence and a weak flow acceleration. In fluid mechanism, understanding turbulence in incompressive Newton fluid is vital, especially in free stream regions where no walls or mean velocity gradient influence the flow. Free stream turbulence still shows complex behavior in turbulent kinetic energy and viscous dissipation. Recent research used wind tunnel to reproduce and analyze um, unbalanced free stream turbulence, aiming to improve turbulence models for simulations and engineering applications. However, challenges like experimental errors and flow non-uniformity remain. Past study often used cylinders to investigate blockage effect. Today's study focused on how weak blockage influence nearly isotropic turbulence using smaller acceleration levels than previous experience to better simulate ideal free stream conditions. Wind tunnel blockage cause flow acceleration near boundaries, which ideally should not affect the core free stream turbulence. However, to confirm this, quantitative verification is needed. Past study focused only on a acceleration region and did not assess other area, or nor did they verify the assumption of isotropy in turbulence models. This reveals uncertainty about how domain selection and isotropy affect modeling accuracy. This study aims to define a computational domain that better maintains isotropy consistent with model assumption. Using large edge simulation, we reproduce steady turbulence in a periodic cubic domain with mean flow acceleration. Unlike the Capson model, which draws special scale information by deriving eddy viscosity from turbulent kinetic energy and its dispersion rate, LES allows more detailed turbulence analysis. This study examines how wind tunnel blockage influenced acceleration impacts turbulence using a model based on the Capson framework. The model describes the effect of acceleration on turbulent kinetic energy through an influence fraction F and decay experiment n for n. For n equals 0, the function simplifies using the non-dimensional acceleration rates s and coefficient p0, which depend on anisotropy A defined from velocity fluctuation u v double. When the turbulent is isotropic A equals 1, then P0 equals 0, and F equals 1, which S equals 0. The mean velocity field incorporates acceleration rates S and satisfies the continuity equation. This study reproduced weak asymmetric acceleration in the x direction applied from non-dimensional time 100. In previous study, a cubic computational domain with side length 2π was used, containing only acceleration regions. In contrast, this study adopts a periodic cubic domain with side length 4π composed of alternating 2π, accelerating and decelerated subdomains. This paper focused on analysis within the accelerated region. Since the moderate turbulence wavelength is smaller than 2π, there is no interference between adjacent regions. Grid resolution is defined per 2π for both setup to ensure consistency. This analysis uses the continuity and Navier-Stokes equation with additional external force terms. The instantaneous velocity is decomposed into mean and fluctuating components, and the governing equation for the fluctuation are applied. External force, large F and small f, are introduced to produce acceleration and maintain steady turbulence. The acceleration force is defined by its components, while the steady forcing, small f, is given by its large f with small c equal 0.133. The spatial scale is set to 4 based on prior studies. Large simulation is employed for detailed turbulence analysis. Based on prior research, this study used a first-order central difference scheme for spatial discrimination and a second-stage fourth-order longitudinal method for time integration. The Smagorinsky model is applied with a contract, and the Reynolds number is set up 222.667. The filter-wise defines the eddy viscosity. Simulation ran until non-dimensional time 1000. Its acceleration applied from time 100 and the time setup time step of 0.005. Three acceleration rates are tested. Non-acceleration S equals 0, baseline 0.01, and triple baseline 0.03. Stationary turbulence is generated at a spatial scale of 4. Grid setup includes uniform divisions 16 and 32 per 2π, and non-uniform grid with 16 in a main flow and 32 in others. Figures show the time scale of turbulent kinetic energy under previous and correct conditions. From low acceleration rates s equals 0 or 0.01, both setup maintain steady energy, showing weak acceleration has little effect. At s equals 0.03, panel A shows a sharp rise and peak near time 400, while panel B shows only a slight increase, indicated more stable turbulence. Comparing case with equal grid dissolution, the correct setup produces energy level closer to s equals 0, even at higher acceleration. This suggests that alternating acceleration deceleration domain suppress moderate deviation better, aligning more closely with the K-epsilon model assumption and the influence function. Figure A and B presents normalized turbulent kinetic energy with a grid resolution of 32 points per 2 pi in all directions. Normalized, normalized by the zero acceleration cause value equal 1. Under this study's condition, the value at s equal 0.01 remains closer to 1 than in previous research. A indicated better aligning alignment with model assumption. A key assumption is isotropic velocity fluctuations. Figure C and D show the isotropic indicator F, where F equals 1 indicates perfect isotropy. For S equals 0.01 and 0.03, this study set up D yields F values closer to 1 than the previous setup C. Moreover, F recovers after decreasing, unlike in previous conditions, suggesting enhanced isotropy and better model consistency. Figure A shows turbulent kinetic energy over time from previous research, and Figure B shows results from this study, both with higher grade solution only in the streamwise direction. At acceleration rates s equals 0.01 and 0.03, this study's results remain closer to the zero acceleration baseline, indicating more stable turbulence. Figure C and D display the entropy indicator. At s equals 0.01, both setup shows value near 1, meaning high entropy. At s equals 0.03, the previous setup entropy drops significantly, while this study maintains values near 1, showing better entropy. This result demonstrates that even with only streamwise grid refinement, the modi- modification in this study improved prediction of turbulent kinetic energy and isotropic compared to previous work. Figure A shows that normalized turbulent kinetic energy using a uniform grid of 16 points per 2 pi in all directions, while figure B used 60 points in the x direction and 32 in the y and z direction. In both cases, little variation is observed across different acceleration rates. Figure C and D presents the isotropy indicator. F for uniform and anisotropic grades, respectively, also showing manual response even at S equals 0.03. This insensitivity reflects grid dependence, where increased subgrid scale and viscosity masks physical difference. These results suggest that the resolution of 16 points per 2 pi is too close to detect acceleration effect or entropy changes reliably in turbulence analysis. This study aims to quantify residual perturbation in homogeneous isotropic turbulence and the weak substantial mean flow acceleration typical of wind tunnel blockage effect. This grid distribution setup were tested across two domain configurations and Compression is performed under the following different split conditions. Uniform grid solution in all directions. This is an in prior studies. And increase resolution only in the streamwise direction. And closer resolution in all directions than case 1. In case 1, this study's domain produced results more consistent with the K-epsilon model than previous research indicated improved accuracy. In case 2, streamwise focused resolution improved model agreement under certain conditions. In case 3, false grids caused insensitivity to domain difference and reduced model conformity. This finding confirmed that adequate spatial resolution is essential for accurately capturing the effect of weak acceleration on turbulence. Thank you for watching.